last week we looked at motion, looked at some of the terminology that we use with motion, especially vectors and how you work with vectors. And then we started to relate that to forces. What we're going to do today is look at some more of the effects of forces. We're going to look at things such as work, doing work and transferring energy, the rate of transferring energy, power. Then we will also look at stresses, which includes pressure stresses, so stresses on the surface area of objects, and then material stresses, so where you have forces affecting the material inside. Starting up by looking at work, energy and power. Work done is when you transfer energy to an object, or some object transfers energy to another, and that's the effect of forces acting on them to do that work. And work done is equal to the force that you exert on some object multiplied by the distance moved in the direction of the force. So W equals Fd, and the unit for that is the joule. You can transfer energy slowly, and you can transfer energy quickly. So the rate at which you transfer energy we call power. Power is work done divided by the time, rather. And the units for that is the watt. Let me give you an example of power. That's my car, Ford Focus, right? 73 kilowatt output. However, you can get faster cars or more powerful cars. The Bugatti Veyron, 883 kilowatts. The point of that is, the Bugatti Veyron, that can transfer more energy per unit time than my car. So if I'm stopped at the traffic lights, then that one's going to get up to a higher speed and therefore have more kinetic energy in a much shorter time than I am off the lights. So the Bugatti Veyron is going to demolish me off the lights. Let's look at some particular types of energy. We've got gravitational potential energy. This is to do with gravity doing work on objects, or us doing work against gravity. So that's the same thing going in different ways. Here, what we're going to do is increase the height of this object, which has got a mass m, by using a force F. And if we assume that there's no energy losses, then the force required to do that will be equal to the weight. So we've moved it up a height of h. The work that I did against gravity in moving that object height h is force times, or F times h, so it's the force of F multiplied by h. Now the force was equal to mg, it's equal to the weight. So therefore, the work done against gravity was mgh, and that's where the equation comes from. Okay. Once I've lifted it up there, gravity then will have the potential to do work on that object. That's why we call it potential energy. As soon as gravity's not going to do any work on that object until I let go of it or release it in whatever manner. So the potential energy is mgh. This notation here, E subscript P, is what's used in the data sheet for the exams. Okay, or the form of the book. So that's gravitational potential energy. Then on to kinetic energy, which is the energy associated with motion. What we're going to do here is accelerate an object to a speed v. That's going to be its final speed. So there's my object there. It's got a mass m, and the force that I'm going to use to accelerate it is F. So I accelerate it up to speed v. And the distance over which I do that is s. Distance of s. Now, F equals ma. We learned that last week. So the work that I did is for F times s, and because F equals ma, then the work done is MAS. I can use the SUVAT equation here to relate acceleration S, the displacement over which I accelerated it, and the final velocity. Because u was 0, then u squared is 0. And then I rearranged it to get a substitution for AS. So AS is equal to a half v squared because the u squared term there is 0. And the work done then is a half mv squared because I'm replacing the AS here with the half v squared there. So I've got my term for kinetic energy. You don't need to know that derivation, I'm just showing it to you because it's there. So kinetic energy, that equation is in the formula book as well, in that notation, E subscript K. That is gravitational potential and kinetic energy. Whenever you transfer energy from one form to another, this principle of conservation of energy applies. Energy cannot be created or destroyed, it can only be transformed from one type to another. And that principle is the result of the work of many chemists and engineers over history. Lots of people contributed to that knowledge. Here's a simple energy transfer diagram. Chemical is transformed into heat and electrical, or electrical and heat. One of those forms of energy is useful, the electrical, and in this case the heat is not useful, but it's there. So if I have a cell or a battery and I use that in some electrical circuit, then I get some electrical energy from that chemical energy which is stored in the cell. But as a byproduct of doing that reaction, I get some heat. So the cell itself gets hot and the circuit also heats up. So it's an inefficient transfer process because things get hot. So that energy is there nonetheless, that heat energy. So this is showing that the electrical energy didn't come from anywhere. I didn't create energy to have that electrical energy. Also, I didn't destroy energy if all of my chemical that I carefully put into my cell isn't transferred to electrical, because some of it got transferred to heat, so there was no destruction of energy either as a result of that. Energy in freefall. Let's start applying our knowledge of energy and energy transfers to cases such as this. What happens during freefall is that gravitational potential energy is transformed into kinetic energy. And if we have no energy losses, then all of the gravitational potential energy that I have at the start will be transformed into kinetic energy after that, the freefall. So starting potential is the final kinetic. If it's starting from rest, then the starting kinetic energy is 0. That object free falls, and afterwards it's got no potential energy. Now, potential energy you always have to measure from a reference point. So if I just take its lowest point as my reference point and I say it has 0 potential energy relative to that point, so then the kinetic energy is equal to that total amount of potential energy from there. Then when it hits the ground with a velocity. It's quite common for students to tell me that an object, when it free falls, hits the ground with 0 velocity. Well, it hits the ground with a velocity, but the table decelerates it so that it has 0 velocity not long afterwards, in a very, very short space of time afterwards. So don't make that mistake, it hits the ground with a velocity. Right, so if the kinetic energy here is equal to mgh, then mgh equals a half mv squared. Gh is equal to a half v squared because the masses cancel out on both sides of the equation. And if I rearrange that for v, then v equals root 2gh. Now that's the same result that SUVAT would give you actually. so that you see how physics is consistent if you use the Seebeck equation for that. That's energy in freefall, so let's do energy in projectiles. During projectile motion, the projectile starts off with a lot of kinetic energy, and then it gains height if it's a general projectile that's projected at an angle from the horizontal. And then that kinetic energy, some of that anyway, is converted into gravitational potential energy, and then it converts that gravitational potential energy back to kinetic energy on the way down. So it's slowing down, but gaining height, and then it loses height and gains speed. There's our trajectory, and if there's no energy losses, which we will assume here, then the starting kinetic energy is equal to the final kinetic energy. At the start, we have a minimum potential energy, or you can define that as zero potential energy, but it has maximum kinetic energy. So it's going as fast as it will go at this point here. So it's launched with maximum K. Up at the top, the potential energy is maximum because it's reached a maximum height. It's not going to go any higher, so it's a maximum potential energy. And the kinetic energy is minimum. Now here you can't say it's zero. A lot of people make the mistake of saying it's zero. It didn't suddenly stop. It didn't come to zero velocity at that point. It reaches that point and it has velocity. How do we know that? Well, from our knowledge of projectiles, we know that which aspect of the velocity is constant? Horizontal. So if it's constant, it can't magically be zero at the top and then come back to being what it was at the start. So horizontal component of velocity is constant all the way through. So that at the top, it does have velocity. It is still moving at the top. The only exception to that is if you have a vertical projectile. So a vertical projectile has a zero component of horizontal velocity throughout its flight. So therefore, when the vertical component is zero, its total velocity is zero. And then back at the ground again, on the other side though, the potential energy is back to minimum or zero, and the kinetic energy is maximum. Over here, this is where we have the kinetic energy being converted into GPE. Note that it's not all of the kinetic energy because it seems to have some kinetic energy here. So there is a transfer of some kinetic energy to potential energy, and then all of that potential energy that it gained is then converted back to kinetic energy. Any questions so far? All right. Efficiency then. So this is taking into account the fact that there are energy in our energy transformations. Some of our energy doesn't go to a type of energy that we want. Efficiency is equal to the useful output, that's what we're interested in, divided by the input times 100. So it's a percentage, and the higher the percentage, the more efficient, and what we mean by that is we've got more of the energy that we want coming out of that process and the smallest amount of waste energy as possible. Most common waste energy is heat, as I'm sure you're well aware. You can measure efficiency in energy or power, but if you do it in energy, then both of these terms need to be in energy, and if you do it in power, then both of these need to be in power, so make sure that your terms are the same type. So there you see the units cancel out, and therefore you can talk about percentage. That's a Sankey diagram, and that's a good way of visualizing the efficiency of a transfer. The width at each point indicates the proportion of energy that is going to that aspect of the diagram. So here you start off with 100%. That's the maximum width. Now you can't have this plus this adding up to more than that, because otherwise you would have created energy. And you can't have this and this, adding up to less than that, because otherwise you would have destroyed energy. So the width tells you the proportion of energy. That's how much we start off with. Then some of it is diverted down here. That's our waste. Whatever's diverted from going straight across is our waste. And this is what we're left over with is our useful energy. So the Sankey diagram visualises it. Now, that's a very simple Sankey diagram. In reality, you can have much more complex ones. Take, for example, the energy flow for a whole country, like the UK. That's the UK energy flow diagram from 1974. You can see there's a heck of a lot going on there. So you don't have to be able to read everything, but you can just see how some of this energy goes over here and some over here and so on. So you've got lots of energy pathways. So it's an amazing way of visualising and seeing energy. That's 1974. You notice quite a large proportion of coal there. Take a more recent one, 2012, and you have much more gas, much less coal, and so the energy flows are different there. Don't worry, you won't have to draw an energy flow diagram quite that complex in an exam. Friction and heat losses then, let's start considering something a little more related to the real world. All energy conversions in the real world are less than 100% efficient. And that is usually because of things like friction forces, and they do work against our motion. So you can have friction between surfaces, and you get this kind of friction in wheels, axles, even on your shoes. So as you're walking along, you're generating friction. You're heating up the road or the corridor slightly. The point there is you're not going to reach down with a thermometer and measure how much hotter the ground got, because that energy is dispersed, but it is there. There is some heating of your shoes and of the surface as well. In fact, if the friction is very high, you can get things getting very hot. I remember once in my car, the brakes were faulty, and so there was an incredible amount of friction, and I stopped and I put my hand near the wheel, and it was radiating heat. You could feel it, it's so hot. And then I got a bucket of water and chucked it on there, and it was steaming away. So friction generates heat, it's real, and even if you don't immediately notice it. Then you have fluids as well, so drag in fluids. Friction in fluids we call drag, and you can have that, we often refer to air resistance, drag from water, so that would apply to boats, but air resistance is the main one that you'll need to be aware of. So friction gives rise to energy, some of your energy from the input being converted into heat, which is a waste. In all cases, energy is converted to heat from those. Let's have a look at some example calculations for work done. First one, we're going to drag a mass up the slope with no friction. So it's frictionless surface, frictionless mass. All we're doing is work against gravity. We've got a 30 kilogram mass. We're going to use force F to drag it up the slope. And the slope has an incline of 10 degrees. The distance over which we pull it up the slope is 100 metres. So, first thing we need to do, because we're doing work against gravity, is work out the height through which we lifted it by dragging it up here. So that's equal to 100 times sine 10. That's using trigonometry. We know the hypotenuse of the triangle, and we want to find the opposite. So it's 100 times sine 10. That's 17.4 metres we raised it up. The work done, not work done, the weight is 30 times 9.8, so that's mg, and that's 294 newtons. So the work done is 294 times 17.4 should be, so it's about 5.1 kilojoules. That's how much work we did dragging it up a frictionless slope. Didn't need to worry about this distance here, remember the definition of work done. Work done is equal to the force times what? In the direction of the force. Now what's the direction of the force here? It's actually, again, the opposite direction of the weight, so it's vertical, isn't it? So that's why we need to use this distance here. Alright? Example 2. Now we're going to go down, we're going to let our mass go. And we want to find out how fast it's travelling when it reaches the bottom of the slope. The average friction is 22 newtons. The work done lifting it up the slope, I've left up here so we know what work we did against gravity dragging it up there. It's 5.1 kilojoules. The potential energy is equal, the gravitational potential energy is equal to the work we did lifting up the slope, right? So that's 5.1 kilojoules. The work done against friction is the friction force multiplied by the distance that it's actually moving. Now the friction force is parallel to the slope. So therefore, that's where this distance is going to come into play, this 100 metres, because this is the distance moved in the direction of that force. And that is 2.2 kilojoules, so that's 22 times 100. The kinetic energy that it will have at the bottom is equal to the difference of those. The work that gravity is going to do on it, pulling it down the slope, and minus the work done against friction. So then that's 2.9 kilojoules. Just do 5.1 minus 2.2. 2.91. 2.2, yeah. The velocity that the mass will have at the bottom is then found by rearranging the kinetic energy equation. So V is equal to the square root of 2 times the kinetic energy divided by the mass. And when you work that out, it'll be 14 meters per second. That is less than what it would have if there was no friction. If there was no friction, then it's just going to be constant acceleration all the way down there, and you would find the velocity from using that energy in that equation there. Okay, any questions about that? That kind of calculation is quite common. All right then. Drag in free fall, so this is where terminal velocity comes in. Drag depends on velocity. So that means that drag is directly proportional to velocity squared, and that constant k will be given to you if you need to use it. For example, drag equals 0.3 v squared, so the 0.3 is the value of k in that case. If you have free fall, then with a velocity time graph with no drag, you would get something like this. So this is constant acceleration. There's no drag, so the only force acting is the weight, and the weight is equal to the resultant force. So constant acceleration, constant gradient, that's the no drag velocity time graph. But here's how drag changes things. So a velocity time graph that has drag, that's what it would look like there. Okay? So Vt being your terminal velocity there. Alright? As the velocity of the object increases, so does the drag. And therefore, the resultant force, which is equal to the weight minus the drag, that decreases. And that gives you a decreasing acceleration. So let's look at the gradient. The gradient is equal to the gradient of the no drag line immediately after jumping from the aeroplane if it's a skydiver, or immediately from releasing the object if you're just free falling an object. That's because the gradient gives you the acceleration. So the acceleration immediately after release is equal to g, a equals g. But then it decreases, so let's start to annotate this. Initially, the acceleration is equal to g. Then, in this period here, acceleration is less than g, because it's starting to decrease, isn't it? So the gradient is decreasing, the acceleration is decreasing. We looked at that last week. And then, you have zero acceleration when you reach terminal velocity. Terminal velocity, constant velocity, so therefore the acceleration is zero. That's the terminal velocity graph. And the reason for this is, initially, drag is zero because your velocity is zero. Then your drag starts to increase, and therefore your resultant force is decreasing, which is weight minus drag. Eventually the drag will equal the weight, so you've got zero resultant force, zero acceleration. Okay? Yeah, when ordinarily, if you think about the energy conversions that are taking place, ordinarily with no drag, you have a pure GPE to kinetic energy conversion. But when you have drag, some of your GPE is being converted into kinetic energy, so you're gaining velocity. But also, then some of it is also being converted into heat, so you have more and more being converted to heat as you get faster and the drag force gets larger, until eventually you don't have any GPE to kinetic energy conversion. You have a GPE to heat energy conversion taking place when you're at terminal velocity. Alright, drag in projectiles. How does drag in projectiles change things? Firstly, the horizontal velocity is no longer constant. Secondly, the vertical acceleration is no longer constant. Note, horizontal velocity is no longer constant, because that's what was constant in ordinary projectile motion. The vertical acceleration is no longer constant, because that's what was constant in ordinary projectile motion. That's our projectile trajectory with zero drag. This is what it would look like with drag. What's changed is that the maximum height has been reduced, so it doesn't get as high as it did with zero drag. And the maximum range is reduced as well, so it didn't get as far as the zero drag projectile did. When you look at effect 1, you have it's slowing down from the horizontal component of velocity. It's getting less, so you have a deceleration. Okay, and because it's slowing down, drag is related to speed. Therefore, that would be decreasing. So it's decreasing deceleration. Effect 2, if you look at that, on the way up, you have a decreasing deceleration going up, but it's bigger than if there was zero drag, because you have drag in addition to the weight. So on the way up, weight acts down, but because the vertical component of velocity is directed upwards, the drag is also directed downwards. So that's adding on to the weight. But it's getting smaller because that vertical component of velocity is decreasing. And then a decreasing acceleration coming down. Because on the way down, you have your weight acting down, but the vertical component of the velocity is acting down, so therefore the drag acts upwards. And that will be getting faster, so therefore the drag will be getting larger as it comes down. So you also notice it reaches the maximum height earlier than the zero drag version does as well. And the trajectory is also no longer symmetrical. So this is no longer symmetrical, whereas this is symmetrical. Anyone got any questions about that? And that's a fairly complex concept to take in. I'll just remind you then of the key things, which were maximum height is reduced, maximum range is reduced. Actually describing the motion between these 2 points and these 2 points, that's just additional information. Stresses then, so we've done work, power and efficiency, and I've given you some applications of energy into other examples we looked at last week, free fall and projectiles. Right. Stresses then, pressure and material stresses, they're normal stresses. Doesn't mean that you have abnormal ones and normal ones, just means normal in the mathematical sense, force applied perpendicularly per unit area. So we've got a force here acting over this area here, area A. All of them have units of newtons per square metre, or pascals would be the practical unit. Pressure, that's the result of fluids acting on surfaces of objects. Material stresses, that's a result of tension within the material, so within the atomic or the molecular structure of the material, that's what material stresses are. That's the force that gives rise to those. Pressure, force over area. So force applied perpendicularly per unit area. Here's an example of two pistons. I've got force 1 acting on this piston, force 2 acting on this piston. You can see that the areas are different, but because this pipe connects the two, the pressure in both chambers is equal, equals P2. So we're going to apply a small force on the small plunger, right, which has got a small area. Therefore, that will move F2. We'll get a larger force over there because pressure, force over area. So if you rearrange that, pressure times the area will give you a larger force because the area is larger here. So P times the larger area gives us a larger force there. That's a principle which is used in things like car braking systems. So that's a way that you can use pressure to help you out apply a larger force. Pressure is related to fluid depth. Density, we'll need to cover that in order to understand how you arrive at the equation that relates pressure and depth. Density is mass divided by volume. We use the symbol rho to stand for density, so rho equals m divided by v. The units are kilograms per cubic metre. Now the pressure of a fluid depends on the weight of the fluid that's above that point that you're measuring which. So that's why it's related to the fluid depth. Let's take this volume of fluid here. It's got an area on the top of A, and it's these sides are vertical, so therefore the area on the bottom is the same. So we want to know what the pressure is at the bottom here. And the depth of the fluid is equal to H. Pressure is force over area. The weight is providing that force, so F equals mg. The mass of the fluid is equal to, if you look at this equation, rho times the volume. And the volume is equal to this area multiplied by the depth. So therefore M equals rho A H. Pressure is equal to this term multiplied by G divided by A. So the A's cancel out there, leaving us with P equals rho GH. Alright, that's the derivation of that equation there. Let me show you a video showing you how going extremely deep can lead to extreme pressures that you have to cope with. This is going down to the Marianas Trench, 7 miles down. That is serious depth, that's 7 miles down. Now you can't just get down there easily, it's a massive engineering feat to get down that deep. That's deeper than Mount Everest is high, so you saw that there. Mount Everest is 5 miles up. This is 7 miles down. It was done in the 60s, but no one's been back for a long time. And when they went in the 60s, they didn't see much because they hit the ground a bit too fast. So they kicked up loads of silt. So they wanted to go back and see if they could film. There's a big challenge on. And you notice the special submarine that he had to be in to cope with the extreme pressure as a result of all the weight of the fluid above, the water above, acting on the submarine. So that is pressure and depth. Let's start to talk about the beginning of stress. This comes with Robert Hooke, 1635 to 1703 in England. From him we get Hooke's law. So he started looking at the relationship between pressure and extension. So Hooke's law is that the extension, X, I'm going to call it X, I know sometimes we call it E, but I'm calling it X because X is the symbol which is used in the formula book. So extension X is directly proportional to the force applied, provided that the elastic limit has not been reached. And from there you get F equals Kx, where K is the force constant. We mustn't confuse extension with length. Extension and length are different. So this is extension. This is, if you extend something and you measure the length of that object, then you must subtract from that the original length to get the extension. So this is what length is there beyond what it was originally. If we take our object here, which has an original length of L, and we apply force F, then we have extended it, so that now the new length is that, and this X is the extension. Right? If you plot F against X, then you'll get a straight line through the origin, because the law is that the X is proportional, directly proportional to F. The gradient of this line here, with the axis plotted like this, is equal to the force constant. And the force constant indicates the stiffness of the material. Therefore, if you have a steeper line, you have a steeper material. Technically, it's not actually the material that we're talking about the stiffness of here. It's an object, like a spring. So this wouldn't transfer. You couldn't use this to compare one material with another. So you can compare a steel spring with a copper spring, because different materials, different sizes, different shapes. We can use this to talk about the energy that's related to extending materials. When we extend materials, we do work on them. So there's energy transfer involved. And the strain energy, the work that we did on extending material, therefore if there's no energy losses, which there invariably will be, but if there were no energy losses, then this is the potential energy that that extended object could do returning to its original length. That is equal to the area under your force extension graph. So half base times height, that would give you a half fx, and if you replace f with, or from Hooke's law equation, f equals kx, then you get a half kx squared. So you don't even need to know what force you applied. If you know the force constant, then you can just multiply that by the extension squared. Stress and strain is more useful because here we start taking into account things as cross-sectional area and the original length. So with the force constant, you can't compare one material in principle with another material unless you have all the dimensions exactly the same. So you can compare one spring with another, but not, you can't actually talk more generally. So that's why we use stress and strain. Stress, now you don't need to know the sigma and epsilon notation that I'll give you, but so in the formula book you'll just be stress equals Fa, but because of my engineering background I use those. Units are newtons per square metre or pascals, as we already noted. Stress is force over cross-sectional area. Stress can be tensile, so when you apply tension to stretch a material, make it longer. It can also be compressive, so if you apply your force and shrink the material, then you have compression. Strain is x over L, so that's extension over original length, and both of these will have units of meters, therefore leading to strain having no units. It's just a ratio of lengths. So stress, you'll notice, accounts for different cross-sectional areas. So this tells you about the distribution of force within the material, which the force constant doesn't do. Stress-strain graphs. At low stresses for most materials, Hooke's law would be obeyed, and that would give you a straight line in your stress-strain graph, such as that. So that would be at low stresses. And from there, from this straight line portion, you can determine the Young's modulus for a material. Young's modulus having the symbol capital E. And Young's modulus is a measure of the stiffness of a material. If you have a steeper line, you have a stiffer material. If you have a shallower line, then you have a less stiff material. Now, E, Young's modulus, is equal to stress over strain. So stress being equal to F over A and extension being equal to X over L, then the Young's modulus is equal to FL over XA. If you're happier with using E for extension, then it would be over EA. Here are some values of Young's modulus to give you some context to the kind of numbers you may be required to calculate. Steel has a value, these are all in pascals, 2 times 10 to the 11, copper 1.2 times 10 to the 11, glass 6.5 times 10 to the 10, polythene 2 times 10 to the 9. Right, so you can see steel, largest value out of all of them, so it's a stiffer material. Polythene is the least stiff out of all the materials. If you wanted to know what the area under is equal to, this is equal to the energy per unit volume. That is additional, you're not going to need to know that, but it's the energy per unit volume. The area here is a half stress times strain, which is a half Fx over AL. And AL is equal to the volume. So that's, and a half Fx is the work done, if you remember, from the strain energy graph that I showed you. So you've got work done divided by volume, so work done per unit volume. Now, so that's not required knowledge. This was looking at a general stress-strain curve at low stresses. Most materials, they have a straight line portion. But because of the different atomic and molecular structure of different materials, when you actually go up the increase of stress, then you get different graph shapes. So that's what we'll look at now. But before we do that, we'll need to know some terminology. Stiffness, that's resistance to changes in size or shape. Elastic materials return to the original shape or size when the load is removed. Plastic does not return to its original size or shape when the load is removed. You'll notice I've underlined when the load is removed. That's the key thing. You have to remove the load, and then it will have the opportunity to return back to its original length. And materials that deform elastically usually have a straight line in the stress-strain curve. The ultimate tensile stress, that's the maximum stress that a material can take. Alright, so let's look at brittle materials, graphs for brittle materials. These materials are defined as fracturing with zero plastic deformation. They do not deform plastically. So that's a brittle material, just a straight line portion, and then this is where it fractures. This is a stiffer brittle material, again fracturing there. Glass and cast iron are examples of brittle materials. Okay. And the reason for this is that the internal structure prevents any dislocation of the atoms or molecules. So there's no potential for things to slip and slide past each other. Ductile materials, material type 2 you need to know. A ductile material is one which can be drawn into wires. And that's what typical ductile graph will look like. This is the point at which it fractures. You can see that that's not the maximum stress. The point at which it fractures, it's gone beyond the maximum stress, and then stress started to decrease. Because of this plastic deformation of the material, you could continue to strain it at lower stresses. Ductile materials exhibit an elastic behaviour up to the elastic limit. So we've got a straight line here, and that's where you would determine the Young modulus for your material. There's a yield point, so until the yield point, the gradient is still fairly high, so it's still quite stiff. But beyond that, the gradient decreases, so you start to get larger amounts of strain per unit stress. Ultimate tensile stress is there, so that's the maximum stress that material can take. After that, you can actually decrease the amount of stress in order to continue straining the material. Copper and silver would be examples of ductile materials. So these, metals. A lot of metals are ductile. Under normal conditions, that is. If you start heating them up a lot or freezing them, then they behave differently. And lastly, we have polymeric materials. Polymeric materials are ones where you have molecules which are repeated in long chains. So long chains of repeating molecules, that's a polymeric material. This is because the amount of work required to strain that material, to extend it, is different to the amount of work done when it's decreasing to its original length. Therefore, we have to distinguish between a loading curve and an unloading curve. Now, you'll notice that it starts off quite stiff, because it's got a steeper gradient. Then that starts to decrease. And the reason for that is, at this roundabout here, the chains in the material, which were all bundled up, they start to unravel. So when they start to unravel, it then is not so hard to continue straining them. But then once they've unravelled, the stiffness will increase again. If you fractured it, it would fracture up here somewhere. If you then unloaded it around here before you started straining the actual chains themselves, then you may well get it to unload back to its original length, depending on the type of material, because you can have different types of polymeric materials. So rubber would do this. Rubber is a natural polymer, so you get it from trees, sap of trees. If you continue to strain it further and then started to unload it, you might get a curve like this. Now, in both cases, the area under the graph is different, so therefore the amount of work done loading it was more than unloading it. And the reason for that is the molecules rub against each other, there's friction there, there's heat generated, so you do more work extending it than allowing it to return to its original length, or to return to permanent deformation state. So those are possibilities for loading and unloading polymeric materials. Two materials, rubber I mentioned, that's a natural polymer, and polythene is a synthetic polymer. Are there any questions about that? No? Here's an example of high pressure causing high stress in a material, and we'll finish on this. You're going to see an object with being able to exert a lot of force onto a material over a small cross-sectional area. So, high pressure, it's a bullet from a 50 cal rifle, a Barrett 50 cal. Incredibly large force exerted on a small area, causing incredibly high stresses. Now, even if it wasn't a bullet hitting it, if it's something larger and exerting the force over a larger area, sure it'd smash it, but you wouldn't get anything quite as dramatic as that. Yeah. 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 If they used a brick phone, yeah. Yeah. But they probably weren't shooting a bullet as big as this and with as much power in the shell as this. So I don't know if a brick phone would have saved their life from this particular bullet. Okay, that's That's it for today. Any questions to finish up on? Or? No? Alright. So I'll see you next week.